What is it? Today is 2020-03-18. This is a class number 18. Wow, there's no space here. So basically we're gonna pick up from yesterday. We left off at this paper. We will continue. So let me just paste so we know that is class number 18. Yesterday I actually uploaded the handout, the paper, this paper, which is authored by Ce72.51. So I hope that everybody must have access to that. I drop it on the Google Drive, and you have access to that Google Drive already. So all the course materials and the papers, that there's going to be a lot more coming on to that location. Wow. Well, a lot of comments. Okay, good. I am glad that I'm not talking alone. Okay, so I talked about the first page of this paper yesterday. Ce72.51 made this paper in 1971, 10 years after the ASD column curves in 1961 was published. So the point is that we are focusing on the effective length of column determination in here, and you know that the analysis, which actually is possible for us to do and easy enough for us to do, generally is the elastic analysis with the effects of the nonlinear geometry is integrated in. So the geometric stiffness matrix is used in the analysis. You can turn that features on in SAP, in StatPro, whatsoever structural analysis program you use. But the point is that most of the column we are dealing with are going to fail in the inelastic range. That means the inelastic column buckling is going to be the case, and you have to incorporate two nonlinearities in your analysis. So the first is the nonlinear geometry, and the second thing is the inelasticity, and that is brutal for the practicing engineer. So this paper just help alleviates the pain of the engineers, and we have gone through some introductions. Yura talks about the use of the alignment charts, and the alignment charts employs the ratio between the rigidity of the columns to the rigidity of the beam about the joint. For those of you who are watching, let me know if the sound quality is okay or not. I am not sure if the tuning I have over here is okay. I think it is okay, just okay when we do the class recording, but I have no idea what's going on in the live YouTube. So you can let me know if something goes wrong, the picture is not clear or the sound is not clear, let me know. Alright, so come back to here. So the alignment chart, the sample of alignment chart was given, but we talks about the limitation from the alignment chart. Yesterday we went through the AISC. Let me just bring that up. So AISC specification, Alright, I didn't open it ready, so okay, don't waste the time, go there. But the main limitations for the AISC alignment charts are the elastic actions and the assumption that all columns in the story has to buckle together at the same time. And these two assumptions are not so realistic, and this paper by Yura is going to help us through this pain. Otherwise, you're gonna end up with the curiosity and uncertainty about the use of this analysis approach. And we came across this paragraph and we talk about the allowable column stress, which is a function of the KLOR ratio. And from AISC, for the O1, for the allowable stress ASD1, the transition from the elastic buckling to the inelastic buckling locates at 0.5 Fy. So you come to this picture here, and this is what I mean. So it is this point. If we talk about AISC LRFD 2016, so look at to that code for the column buckling. You will see the transition at this stress ratio sigma critical to sigma y being only 0.39 or approximately 0.4. Okay, and this ratio of 0.5 and 0.4 into different codes are associated with the lambda values around 1.4 to 1.5. Okay. So we come back here. The 0.5 Fy here, if we compute the corresponding KL over R values, yesterday we tried to drop in the figures for the steel grade we use in Thailand. So 1 over lambda square, wait a minute, let me get okay. So yesterday we came across this point here, right? So we want to find the corresponding KL over R ratio, and we substitute, we equate KL over R to this expression lambda pi e over blah blah blah, alright? And the lambda values at the 0.5 stress ratio, okay, is equal to the square root of 2, so 1.414 is substituted in, and then the pi and the square root of the 200,000 megapascal divided by 240 megapascal. Alright, the unit cancel out, and then you end up with the KLOR ratio being the 128. The 128 is pretty close to the given KLOR ratio given over here, which is 126, because the Fy is just 36 KSI and the elastic modulus is in the KSI unit, which is 29,000 KSI. So just substitute that in. Well, we can give it a try, right? Where's my calculator? So I can just drop in the, if we use the A36 grade KL over R, equals to 1.414 pi and 29,000 divided by the 36 grade, right? 36 KSI. I hate the unit. Okay. And then, by the way, AT today is very quiet, which is actually peaceful. 29,000 divided by 36, and there you go, 126. Alright, so you can hit your calculator. This is the KSI unit. KSI. So URI is not fooling us around. This is real. Alright, which means that most of the column in multi-story structure will be in the inelastic range. Yeah, thanks, Sivara 126. Oh, this is so interactive, and I'm checking into the comment. And I told you that we had the inelasticity that comes at the same time as the nonlinear geometry, right? And then the buckling stress is given. Actually, we have been talking about the buckling stress that is actually computed from that pi square E, and then you just recompute the I values, right? So that is a couple lectures back that you have the I effective to the I gross, which means I elastic. That ratio reduces the buckling stress, which is the matter of fact that you have the residual stress, especially the part that is the residual compressive stress in your cross section. So that causes the problem that you do not get the buckling column curve that looks like this one. If you have the cross section without the residual stress, you get the blue line, but the reality is that your residual stress just caused this transition. Okay, yeah, we all know this, but the point is that what Yura tries to do over here, he knows of that fact. The point is that he tries to initialize the concept that will make it friendly for you to use the alignment chart. Well, you might be feeling sort of not that okay, because we learn a lot in nonlinear geometry. We wrote the code for the geometric stiffness matrix, right? So in the last semester, so you might question, and how would I make use of the code for the nonlinear geometry? Of course, I'm going to talk about that later once we finish up the business about the alignment chart. But well, this idea is a brilliant idea of Ura's back at that time. So the ET actually is not real. This is just, say, dummy. It is just a dummy thing. Because we know that the tangent modulus of steel, when it turns into the inelasticity, when it is yielding, it is just zero. You know of that. But the ET over here, it is pretty much like the concept we used to talk about. So if we plot the stress and the strain and average stress of the steel cross section under the compression, you are going to get the curve like this transition zone. If you draw the tangent line, you might call this like a ET. Okay, so the ET is something like just a dummy. Okay, just for the use, it is a little tricky, and Let's take a look at it. So the G, which is used in the alignment chart, is just the ratio between the column stiffness and the beam. So the column stiffness, you take the summation. In reality, you might have the top column being steel, the other column being concrete, whatever. So the formula gives you the flexibility, it gives you the EI over L. And if you think about the EI over L, you remember it is ties up to the rotational stiffness. So you have the 12 EI over L cubed, right? 6 over L square, 6 over L square, 4 EI over L. This part here is actually the rotational stiffness of the frame element. So we just take the ratio between the column to the beam, okay, and the E is there, so we have the flexibility. So if we have the concrete beam, you just drop in the E for concrete. Steel column, you drop the E steel for a column. However, we have all of these. Once you have this flexibility, that means the ET will be the better values to stuff in. If you know that the column is going to be inelastic, then we can estimate the ET and put into the alignment chart, and then you can perform the analysis accurately under this scheme. So let's come to here. So the G, which is the values used in the alignment chart, you have the G at the top and the G at the bottom. So this is the alignment chart for the side sway, non-sway frame, and then you draw the line, and then you check for the K value where the line crosses. Okay, so the G for either the top and the bottom will be determined, and this is the G in elastic. It's going to be given in terms of the elastic G multiplied by the ratio between the E tangent divided by the elastic E. Okay, the point is that how to determine the ET. This is the most critical issue. How to come up with the ET, because you don't really know the behavior, the stress-strain relationships, average stress and strain relationship of the column. How do we get that? So if we take a look at the relationships given over here, the stress, the critical stress might be just expressed in terms of the pi square ET over KROR square. Alright, so you have the reduced modulus, the tangent modulus, and then divided by the elastic buckling stress, which is the F subscript E, given in terms of the elastic modulus, the initial slope, okay, pi square KROR square. The KROR square will not change even though your column turns into the inelastic regions. Pi will not be changed. So finally you end up with the relationships if you divide the FCR by FE. You end up with the ET divided by E. Okay, so this simple relationship holds, and it is given over here at this point. The left side here, actually Uras intends to refer to the actual values of the critical stress to the actual elastic buckling stress. but the actual values still the pain. So he just said that, well, fine, just use the numbers given by AISC. The AISC numbers here is not exactly the same as the actual number. Why? Because AISC, when we talk about the development of the column curve, you remember I said that the factor of safety was already incorporated. So we have the factor of safety incorporated in this given column curve. This is the first thing. The second thing, you have other factors like the distribution of the residual stress over the cross section, that is also there. The initial out of straightness, so the column you deal with will be subjected to the ASTM standard, so the L over 1000 limit for the initial out of straightness applies, and the way AISC came up with the column curve is just add more factor of safety in order to account for the initial out of straightness of 1 millimeter per 1 meter. Okay, so that means the column curves we are talking about is not the real value. It is just the number we use in the design, but it is handy, it is good enough, it is very convenient. So you say, well, just do it, just use this, just equate the ET over T ratio to the FA to the F prime E ratio, and then let's take a look. So FA is the inelastic buckling stress, and F prime E is the elastic buckling stress, which in reality you have this transition, right? So at this point where the KL over R is less than the C subscript C value, you'll be having the inelastic buckling rather than just elastic. But then we can take the ratio between this number to this number. So you finally establish the relationships here. The E subscript T to E is equal to FL or F prime E. And then what you need is the ET. So it is estimated by the ratio F prime E times E, and you know that this ratio is always less than 1.0, because if you are in this on the left hand side of this point, you better get less than 1.0. So the tangent modulus is reduced from the initial elastic modulus. Okay, so we agree that we're gonna use the AISC strength to come up with this ratio, and then since you have the well, this is sort of, how to say, a little sloppy. Forgive my language. For those of you who are not so familiar with my language, it is not friendly language in my class. Well, why did I say sloppy? Because actually it might not be as convenient as this one, because sometimes if you don't have the same values of the E, okay, then you better do it one by one. So you might need to update the E for the column, but you might not need to update the E for the beam. If the E for the beam is not the same material as the column, then it might be a little different. Okay, but anyhow, the intention of this formulation is for the steel frame building. So it is as simple as just dropping in the ratio which is less than 1 and then scale to the G elastic. So you come up with the G in elastic. Now the point is that, wow, look at the participants, and then we have so many friends who are not in this class. Welcome if you want to watch. Alright, hello everybody. Yeah, feel free to join, and if it is boring, just let me know. Poor student, they have to listen to this, and it's gonna be available on YouTube as well. So if you need something to put you to sleep, you can open that YouTube and just, maybe if you run out of the story to tell your kids to just get them to bed, then just open this clip and they will fall asleep very quickly, I'm pretty sure. Okay. So let's take a look at the example of this, the use of this G in elastic. So we're gonna look at this frame. Jura gives us the planar frame system, the column and the beam just given over here. We just need to design this column. So column AB is about to be designed, and what we know from here, the load is given to be 750 kip. Alright. Okay, this is the design curve from AISC. So we have both the ASD and LRFD. This one should be applicable to either ASD and LRFD. You just end up with a little different ratio. Well, if we want to check a little bit about the CC value which is produced by the LRFD, let's take a look. Let's try. So if we substitute the lambda being 1.5, so I take the 128 multiplied by 1.5 divided by 1.414, we're gonna get 135. Okay, so let's put that down. C equals to 135.8 for AISC LRFD column curves. Okay, that's gonna make it more, right? 126, and then for this one 135, so more cases will fall into inelastic buckling if you use the new AISC. It is not that new, of course, it is long time already, LRFD. Right, so look at this design example. So column AB is to be designed, so we have no idea about the size of the column, and force is 750 kips. We use the A36 steel, so Fy is 36 ksi. Only in plane behavior will be considered. For iterative purpose, in the design, assume the column above and below are not significantly different in size. Right. So let's start with elastic solution. Jura's claim that for the elastic solution we will end up with overly conservative solution. I told you yesterday already. Overly conservative is fine in the safety point of view, but it's not fine because you might not have a job. You get two big columns from your design. Your boss will not like that. Your client will not like that. So they want you to have some risk. Okay, so we try the wide flange 14 by 150. The I values about, well, since he mentioned already that the buckling is about just one axis. Let's take a look. You see the cross section over there. Alright, so the out of plane behavior, this is in plane. That means the buckling will be like this. So if the buckling is going laterally like this, you see that this is your cross section. This is the orientation of your cross section, and then the buckling occurs about the major axis, the strong axis of the column. Okay, so we do not consider the minor axis buckling, as it is well prevented, and it is not considered. That's the case. Alright, Ix given, the radius of gyrations given, the areas given, GA and GBs are both given. So what are they? GA and GB, you come down here, you have column and column. He said that the top, the above and the below column are pretty much in the same size. So you sum up, okay, for the point A, you sum up this column. For the point B, you sum up these two columns, and then you divide by the rotational stiffness of two beams for B, and this is for A. Alright, so clean this up. Then this is for the beam, which is already given, okay, in the drawings, and this is for the A. Okay, you have two columns, right? For the beam, you also have two beams. Okay, EI over L. This is your L, the length. Turns out you get the ratio 6.93 for both top and bottom. And then you consult with the alignment chart. If you have the 6.93, this is the unbraced frame. 6.93 is somewhere around almost 7, right? This is 5, this is 6, this is 7, so 6.93 is around 7. You end up with the K values. You have 1, 2, 3, 4, 5. That means each increment is equal to 0.2. So this is 1, 2, 3. Okay. You get 2.6. 2.6, you come back here. Oh, sorry, I think I should delete this page. It is not useful anymore, and it takes time to swipe around. Okay, then I can come directly like this. You just get the 2.55 fine. Actually, there is a formula given in AISC, so you can precisely determine the K equals to 2.55. Right? So the KLOR ratio is determined, and then you can find the FA. So this is from the AISC formula, right? If you have these values, then you drop it in to AISC formula, and you're gonna get the stress ratio. Okay. You're gonna get the FA, the inelastic buckling stress, and then the allowable stress is calculated from the area to the FA. So you end up with 776, which is greater than 750. Okay, you get a good try. This is trial and error. You are just pick up the cross section that he tries already. Actually, before he came to this short calculation, he has tried a lot, and it ends up with this one. So it looks just easy for you, but that's a lot of work beforehand. Okay, so you use the Y flange 14 by 115. Now, if you want to design using the iterative solution, so you start with the cross section given the Y flange 14 by 127. Okay, you have the Ix, which is smaller than before, and etc. etc. So you find this first, the G. Okay, the G is changed because your I is different from before. This I for the beam does not change. The beam is designed under the gravity load. It was supposed to change, of course, because that is designed based on the moment capacity. And then from these G values, you go back to the alignment chart for another time. You end up with the K equals to 2.35. You have 5 point something, right? And 2.35 is this one on the green line. Okay. Then fill in, drop in the values, and you will find that the KLOR ratio is less than the C subscript C. That indicates the inelastic buckling of the column. Now, as you know that it is inelastic buckling, you just need to do this follow the step given by Uras, because the G will be redetermined. Okay, so the G will be determined by using the the K will be redetermined using the G inelastic. So you have the G from here, right? You drop it in here, and then you have the stress FA, okay, which is computed from that KL over R. Alright, FA come from the KL over R. KL over R, this one here come from the G. Okay, you're not confused, right? You get the G, you go to alignment chart, you get the K value. You get K value, you compute KL over R. KL over R will be used in AISC formula in order to find the FA, inelastic buckling stress. You get inelastic buckling stress, and then at the meantime you also can get the elastic buckling stress. You determine this ratio of stress, and then you take this ratio multiplied by G you determined previously, which is 5.72. You get a significant reduction of the G, which is the inelastic G. Okay, and then we move to alignment chart for another time in order to determine the K value. Come back. So you go for like 2 point something. Where is that? Okay, which is this pink line. So from this 2 point something, 2 point just a little, you have the K equals to 1.6. So come back. You can see here K is equal to 1.6. Thus K is already reduced significantly from its elastic value, which is 2.3 to 1.6. When the K value reduced, what happened? You look at the alignment chart, right? You look at the column curve. The lambda here is actually the function of K. Lambda is given in terms of K. So if you move things around, then it is just a linear function to another. That means when K reduces, lambda is reducing. And as the lambda reduces, so if lambda reduces, you come down this way. Am I right? The less the lambda is, the greater the ratio between critical stress to the yield. That's it. Is it good for you or is it bad for you? It is actually good, because you have the higher stress for the design. You have more column capacity, right? So let's take a look here. Further reduction of K can be achieved by continuing to cycle the calculation. So what is that? You get the new K being 1.6, you drop in the 1.6 into here, you get the new KL over R ratio, you get the new KL over R, you use this KL over R in determining what is the equation to find FA. Okay, it is this one here. Alright, so the FA is the inelastic buckling stress, and if we are consistent with Uras, he is talking about the AISC ASD. So for the ASD you use this ratio, the old code, but if you go for LIFD you use this ratio. Okay, so did I answer your question, Navindra? Let me know. Okay, so I'll continue from here. K with the updated K is 1.6. You configure you calculate the KLOR for another time, you get 37. From this 37 you plug it in order to find the FA and FE, which are from AISC ASD 1961 like before. Okay, and once you get this two, you plug it in order to get the estimation of ET over E, and then you multiply by the G value, which is the elastic, which is the one taken from here. Okay, because the elastic G. Okay, good to know that. Okay, thanks Navinda. So the elastic G multiplied by the ratio, you end up with 1.02. 1.02. This is the G in elastic. You go back again. So 1.02 will be somewhere here. This is you end up with 1.3 for the K value. Let me write it down neatly. 1.02 for both. What if I want to go to washroom? Would that bother you? You want to wait? This is 1.3. 1.3 comes back to here. Okay, the K is equal to 1.3 over here. Wow, unbelievable. It's like the whole country is watching me teaching. Okay, it would be good if it is useful for you. Alright, and then a few more cycles. So you just keep going like this. Find the new K, get the new K, find the KL over Rx, and then find the FA, find the F prime E, get the new ratio, substitute the new ratio, and multiply by the G elastic, get the new G in elastic, go back to alignment chart, and recompute for the new K, on and on and on. You end up with K equal 1.0. And this K equal to 1.0 can be the rule of thumb number when you design for multi-story steel building. The column, the K values will be approximately about this number. So you don't need to run inelastic analysis plus nonlinear geometry in order to come up with the right estimation of the K. Just drop in 1.0. This is Ura's study. Okay, so we end up with the Y flange protein 127. So we save some bucks. Your boss will love it. Okay, so let's look through this together. The design example shows that the inelastic approach can produce significant reductions in the effective length factor. When the elastic KLOR is reasonably low, about 50 or less, the actual K is usually converged to 1.0. So this is just a rule of thumb number. If you check, you end up with this criteria, then you can run the quick design or quick estimation of the column capacity using the K equals to 1.0, although no specific rule has yet been established. Yeah, Ura is always tricky, so he has something like this put there, but you at least can run these iterative solutions and then figure out if for your case, if the 50 or less is not met, then you can check for your case what K that you will end up with, but you will save a lot of money by doing this. This observation indicates that columns in multi-story frame can often be designed on the basis of K equals to 1.0. That is, the actual story height studied by Liu and inelastic frame buckling also indicates that in low slenderness range, the side sway and no side sway buckling mode shown in figure 1 converge in contrast to elastic solution. Well, as mentioned before, elastic solution gives you overly conservative solution. Well, if you are a fan of overly conservative design, just use it. But if for some case that you want to check when you overstrength the column already because of that overly conservative design, then you can come back and check with this one. So your column might still be okay if you check in using this framework. Okay, in the moderate slenderness range, the inelastic solution will converge in about 2 cycles. So moderate inelastic range means so it could be somewhere around, this is 120 something, right? And Ura talk about 50 or less, right? And in this range, it's going to take you quite a few iterations in order to get the convergence. So it will converge faster because the difference between the FA and FE are not that large, like the zone where you have the KL over R less than 50. Okay. Now, let's take a look at the buckling strength of the story. Actually, there's a long reading over here, but I can explain all of this in just short, so we don't need to go through that very long explanation. So let me just add a page. Okay, oh, it is already there. So let's look at the page over here. I will draw the frame shown in there. Okay, at the top of the frame, oops. To the audience who are not so familiar with me or with my teaching, I am the OCD kind of person, so you'll be bored waiting for me to get a perfect drawing. So please be patient with that. Okay, at the base of the column we have the fixed support. and we have two columns. First of all, let's consider the first case. It is the unbraced case. We have a question. Milk asks me, sir, if GA and GB are not identical, what is the main different thing from this calculation? Well, there is no difference. It's actually the same. In this paper, it is just a matter of fact that Yuras want to make it easy. He wants to simplify the calculation, so he doesn't want you to spend, well, the paper is just few pages, right? So he doesn't have that much space to stuff in the GA calculations separately and GB calculations. So he just assumed that this is taken from a frame of which the parameters for the A and the B are the same, so it does not waste the line in his paper. It is just for simplicity. That's all about the same GA and GB. But in the reality, if you end up with the different GA and GB, you will conduct the GA inelastic evaluations and GB inelastic evaluation separately. You understand that, right? Did I answer your question? Let me know. The question and the live page is a little bit behind my current time, so I am about 5 to 10 seconds before you. So I'll check if I answer your question properly, and then let me just well, actually I can copy, right? Then I copy and put it on the next page. Take a screenshot, okay, and then copy. Well, you know, Apple should pay me. I think there's going to be a lot more people who wants to buy iPad after watching this video. Alright, okay, Milk, you got it. After watching this video. So, well, I think I deserve the commission for the iPad sales in Thailand. Okay, come back. So we talk about the frame. How can I move it? Image. No. So edit. Alright, and I move it. Okay. So we are going to talk about these 4 cases. Actually, these 4 cases will lead us to the concept so-called sigma p concept. Sorry. Basically, sigma p concept just enable us to compute the entire story buckling load, and the columns are actually work together, but we got to be very careful, because in some case you might not be able to overload the column. That you're gonna see what I mean in a bit. Okay, so we have one frame, and let's talk about the capacity of this frame. First of all, the case A, the frame is unbraced, and at the top you can see that you have that circle dot which represents the hinge. That means you have no rotational restraint at the top of column. And this frame was loaded, so 2 columns buckle simultaneously. What does that mean? The capacity of the column, each individual column. First of all, the column on the left, the capacity is equals the moment capacity. Okay, when we talk about buckling, then we just think about the capacity to reduce the second order moment. Let me drink a little bit. So, left column has a capacity of 100 delta, whereas the second column has the capacity of 500 delta. For this, the K is equal to 2.0 because it is the cantilever column with the free top. And now load is applied, so we have 100 and 500 apply on top of both. So the load distribution is identical to the capacity of each individual column. Okay, and now it buckles simultaneously. Alright, this is just to portray, or just to shows you that this is the first possibility of the failure of this frame. Whereas in the case B, you have the same column, so left and right columns are made of the same thing, but you restrain the top of the column such that the lateral movement at the top is not possible. So what happens? You improve the K values. Okay, when the column buckle, it's gonna buckle like this, and as you improve the K values, you have the condition which is pretty much like pin and pin. Okay, so K is reduced from 2 to 1. That means the capacity will be in the ratio which is 2 square, right? So you have 4 times higher the buckling load when you compare with the first case, 100 to 400 and 500 to 2000. This is the base case that this entire frame can resist. Now, what if we change the distribution of the force? So previously in the case A, we apply forces by following the capacity of each individual column. Now I apply the different distribution. So from 500 here, it is reduced to 300. And then that missing 200 is instead dropped into the left column. So in the left column, you used to have just 100, now you have the 300. The question is, if it is possible to do this, or is it going to be collapse, let's say before this. If I just put not 200, if I just put 100, is it going to collapse? Well, because you found that 100 is the buckling load of the left column, and now we over stress the left column. Okay, will it fail? So this is the establishment of the sigma p concept. The point is that you are eligible to apply up to 200 on the additional 200 on the left column. Why? Once the left column is loaded to 100, this is the maximum resistance, moment resistance produced by the left column. and you will have additional moment which is caused by the 200. So the 200, if we draw the picture, welcome you all. Pigwan just joined. Don't you go to work today? Well, very surprised that there are so many people watching this, right? Okay, we have delta. So the delta multiplied by 100 is taken care of by this 100 delta. You have another part which is 200. Okay, that cannot be taken care of by the spring at the base because you are saturating the spring at the base. Oh, that also join. What's going on at UFM? Let me know. Do I have anything to eat there? So 200 is multiplied by the delta. And if you assume that this part turns out to be the hinge, well, because you overstrain this by the 100 part already, right? So the 200 part will not be resisted by this point here. You have the driving moment, which is 200 multiplied by the delta. And then the thing that prevents this frame from falling down on the ground will be the resistance, which is coming along the axis of the beam. This resistance, how much we can figure out. So as the driving moment is 200. Okay, you first of all, you just group these two up. These two are okay already, right? So I will not incorporate these two into the consideration we are going to talk about. If we take moment about the base point, you have 200 multiplied by delta. That's gonna be equal to what should be the name of this one? F subscript L, which means lateral force. So FL should be multiplied by what? Take moment about this point here at the base. So you need this height. Okay, well, this height is equal to L. So FL is equal to 200 times delta over L. Okay, if you have this force acting on the left column, on the right column you'll be expecting identical magnitude of force, and it's gonna be like the action to this one being 200 delta over L. So this part comes along with 300. We have delta as the deformation used to compute second order moment. So over here at the base, it has the capacity to handle 500 delta. So let's see, the 500 delta is the capacity, and we got to see if the capacity is greater than the demand or not. So the demand should be equal to 300, right? This part here multiplied by delta, and then you add up with another part. The another part is the part that this right column is helping stabilizing the left column. So we take the 200 delta over L, which is the lateral force, and then multiply by the height L. So you get the moment. So the demand moment and the capacity moment, right now it is balanced. You get 500 delta equal to 500 delta. So this system is going to work. Even though you overstrain the left column, but as long as this part that you overstrength is less than the room that you provided on the right column. The room that you provided means the difference between 500 as the capacity to the 300, which is the applied force, the actual applied force. So if you have extra capacity, this extra capacity of the column in the same frame can be used to stabilize the other columns which is under the higher load, so that produce the stability to the frames in the same system, in the same story. Okay, then if you try this one, I'm gonna show you that this is very useful, but you've got to be careful with one thing. So as you have 100 delta and 500 delta, it is possible for you to add 100 with something, and this side here you can have 300 okay, well, which is less than 500. So if you have 100 plus 50, then the resistance back here will be 350 delta. Alright, so this is going to work as long as this part here is less than the margin 200, which is the leftover from this point. So you ask further, I guess. You ask further. So what if I dump everything on the left side like this? If the capacity is 500 for this side, well, what if I put just 100 here, and as I have the leftover from 100 equals to 400, okay, I dump 400 to this point here. Is it going to be okay or not? Now, you'll be ending up with the local buckling if you do so. Why? Because this column under the non-sway, for the left column under the sway mode, it has capacity 100 delta, but if it is not sway, it has 400 delta. Okay, so this is the cap. Unless you brace at the middle and shorten down the unbraced length, this is going to be the cap. If you shorten it down and you change the buckling shape into this full cycle sine curve, you're gonna get probably like 1600 delta. But we are not doing that, right? So we keep the column as it is like this. You have the capacity of 400 delta. That means the column itself will buckle, and it will buckle locally, so just one point here, whereas the other side is still solid. So this side, the right hand side column, is working as the part that produces the stability against the sway in the left column. So the sway was prevented this part does not move, the top part does not move, but you put too much force, so the buckling forms like this locally in the left column only. Okay. So this is the story. He shows this in the case D. So you see that you make it put the small load there and add small load on the left side. Even though you have the frame stability against the sway, but the individual column fails, it buckles. So you still ends up with the failure. So this is a sigma P concept. We have several columns in the frame. And the frame like this are connected together to make one story. So one has F1 capacity delta. You write this like the moment, so you need to times the delta, F4 delta, where F1, F2, F3, F4 are the capacity of individual column against the sway buckling mode, like this. So the sigma P concept say that, well, from the proof above, you can put or you can distribute the load onto these columns. So you have F star 1, F star 2, F star 3, and F star 4, and summation of F star has to be less than summation of F. So summation of F is here. Okay. Regardless of pattern. Or distribution. That's one thing. The second thing, just make sure that F star, let's call F star the Apple Pencil tool is very sensitive to just a tap. I equals to 1 to n, I equals to 1 to n. Okay, so make sure that F star I is not exceeding the brace column capacity. So individual capacity, you just do not overstrain. That will be all. Two rules, two requirements. The sigma P is from this. Sigma is a summation. P will P is the axial force, so sigma P concept. We talked about the quite a freedom to distribute the axial load, but we are not get that we are not that free, let's say. So we are still subjected to the number 2, but it is good enough. We have the leaning column and the other columns in the same system. If they are still not hitting the capacity, they still help stabilize the column that are in trouble in the same story. Okay. So let's go through this quickly if I miss anything in this writing. It is safe to treat separately each column to which beam are rigidly attached and to use the alignment chart. Okay. Sideway buckling is a total story phenomenon. A single individual column cannot fail by sideway without all the columns. Okay. In the same story, also buckling in sideway mode. On the other hand, buckling in non-sway mode is an individual phenomenon. Okay, each column non-sway buckling load is reasonably independent of buckling load of other column. Of course, a quantitative description of frame buckling is presented in Figure 6. I explained Figure 6 already. The frame is unbraced. First, the column sizes were chosen so that both column buckles at the individual load shown in each case. The effective length is 2.0. When sideway occurs, the base moment P times delta are produced. For the given situation, the total load on the frame is 600 and the P delta moment total is 600. So this is the sigma, right? P times the delta. If the frame is braced as shown in Figure 6b, so that case equals to 1.0. This is the braced frame and it leads you to the braced frame capacity. This might be bothering you, I know. The 1.0, you see that this looks like a fixed support, sir. I don't have a good feeling about the 1.0. Okay, don't worry too much about this. When it forms the inelastic buckling fully, then the hinge could also occur, and this is just for a matter of fact that Jura just want to illustrate the problem for you, so he just go with the simple K for the case of the unbraced frame illustration. Each column can carry 4 times the load that can be supported by the unbraced frame. Okay, as you reduce K from 2 to 1, so you have the factor of 2 square multiply. Right, in the braced frame, the maximum load on the left column is 400. So this is the target value that no matter how much you dump, okay, don't exceed the unbraced column. Don't exceed the braced capacity of each individual column, independent of the load on the right column. Well, suppose that the frame is unbraced in Figure 6a, but the column on the right support on the right supports a load of 300, a reduction of 300. This is the margin I mentioned, right? So we have the room, the unused capacity of 200 from its individual unbraced strength. The loading configuration in 60, this column will not side sway until the moment of 500 is reached at the base. So the total capacity is not met yet, and it will withstand until the 500 is reached. So the column has the capability to sustain an additional moment of 200 delta, I mean for the left hand side from another source. Okay. In other words, the right column has a reserve of strength which can be utilized to provide bracing force. Yeah. Actually, my explanation in easy words should be easier to understand. Okay, as long as I don't exceed 200 delta over L. Since the column on the left is now braced, and side sway will not occur until the base moment reach 100, it can be designed with K factor of less than 2.0. Therefore, it can support an additional load of 200. Okay. This is 200 greater than the individual unbraced column. So basically, if you want to look at this in your design practice, you come up with the capacity of 100 tons. If you calculate the capacity that is referred to the side sway mode of the left column, but now as it is braced by the right column, from 100 ton could be above, so you can go to like several hundred tons above 100 because it will not side sway, but less than the capacity as a fully braced non-side sway column, so it shouldn't be more than 400. Note that the total frame load at buckling is still 600. Okay, keep in mind. So that's the sigma p that you cannot exceed. First condition. The second condition is that don't exceed the individual column non-sway capacity. However, the load distribution on individual column is different. To summarize, the shear capacity of column can be replaced by an equivalent. Okay, blah blah blah. Right? Nothing. Okay. So that's just some more explanation, but I just did the explanation for all already. So the rest of this paper, and we are running out of time for today also. So Yura gives you the example, and this is just the same as the illustration, the drawing I just gave you. So design example number 2, which is this one. Design the columns in the structure shows in figure 8. Rigid connections are used only at the exterior column. Simple connections are used at the column. So okay, it is pin, and then rigid. It's braced at the top and bottom out of the plane, blah blah blah. Side sway is permitted in plane but not out of plane. Okay, it's just simplicity. You don't want to talk about another direction, just focus on one direction only. That's it. So column A, we have column A like this. Out of plane K equals 1.0, in plane direct use of alignment chart for the column blah 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 gives the K equals to infinity. K is equal to infinity because at the top over here, when you compute the K, you take the sigma of the EI over L for the column divided by sigma, the same thing for the beam. You have just the column, right? But as it is hinged, then you do not have any contribution from the beam stiffness. So basically you have something divided by 0 that makes the infinity. So you can come up with the K equal to infinity the column is unstable. However, the exterior column can be designed to stabilize the system, so use K equals to 1.0. Okay, from AISC, KL, blah blah, and then you come up with the cross section. And column B, so basically the column B will help brace column A. For now, column A has no capacity at all. You get what I mean, right? Column A has no capacity. It is pinned at the bottom, pinned at the top, so they have no capacity. Now let's take a look at the column B design. Column B stabilizes the structure for side sway in addition to its own load. Each column B must support additional P delta moment, which is 105 delta. 105 come from triple of 70, which is 210, and the B on the sides, they are identical, so they take like the same equal amount or same contribution to stabilize column A. So breaks down into 105 and 105. This is why you have 105 times delta. As shown in figure 9, this is equivalent to an additional axial load on the exterior column. Okay, so basically what you want to do, or what is gonna happen, is that you have 40 plus 105. This is equivalent to this case. Right. So you have 145 keeps in plane only. Determine K from the alignment chart. There is no change out of plane. Since bracing against side sway is provided at the individual column, whatever. Okay. So we determine the G. You have 2G. This case, it illustrates you the different G. Milk, you used to ask me about that, so you can look up at this. Okay, you have G top and G bottom. G bottom is equal to infinity, right? Because it has the column stiffness, but it has no beam stiffness, as the base support is hinge. The hinge condition gives you the zero stiffness for the girder or for the beam. The denominator is 0, then you get the infinity. Okay. For the top, you use the beam, okay, and you use the column, so you have one beam and one column. You get the I column divided by the I beam. What is the 2.0? 35 is the length. 2.0. Okay. Far end of the beam is pinned. So it comes to this is like the moment distribution. And then determine the K from alignment chart and etc. So you just need to come down to this point here, where you get the allowable stress, allowable strength of the column being greater than 145 kips. This is so crazy. 145.2. Okay. All right. Before we finish up, this is just another example. You can just look into it. there is nothing special than the first example. But what I want to, what I would like you to, how to say, the point is that many of us may not be using alignment chart anymore, as it is restrained to many conditions that I explained in the last class already. So this paper sort of focus on the modified G value in order to come up with the G value determination and figuring out the K value in the alignment chart. But again, we might not use the alignment chart. Your structure might not be the same, may not satisfy the condition required by the alignment chart. So what will be the use of this paper? You might feel like, so this is like obsolete already. We are not using alignment chart anymore. We are going to use the structural analysis program. We're gonna use the nonlinear geometry or the geometric stiffness matrix in order to run the analysis, in order to work on the stability issue. This is still useful, but Yura is not saying that, because here, which can be very complex. We talked about this yesterday. Well, this paper is made in 1971, at the time that the computer structural analysis program is not widely used, and personal computer is not widely used as well. But now we can write the code in just MATLAB in Octave to run structural analysis and account for the nonlinear or p delta effect. So we're gonna make this paper useful for the world in the future of the 1971, which is today, 2020. Well, how many years? 1971 to 2020. This 50 years already, right? Still wonder if Yura is still there, alive and healthy. I miss him so much. I never have a chance to go back to Austin anymore after my graduation. This is like more than 10 years already. Oh, no. Okay. So, let's see. We can run structural analysis, and then we can do the iterative solution as well. Alright, you can see the nature of the modification of the G values. It is just the stiffness modification. That stiffness modification gives you the G, the inelastic G. Inelastic G is used to compute the K. So basically, if you look into the framework, which is pretty much the same as running the full-fledged nonlinear geometric structural analysis, you just turn on nonlinear geometry, and then you run the first analysis. Of course, you run the first analysis, you get the distribution of force information. You can revise your analysis for the second step using that FA over FE prime, if you wish. So the FA over FE prime gives you the ET. So you can compute the ET from the FA over FE prime multiplied by E. Right. And then ET, you just stuff this in to your structural analysis program or your FEM. Well, you avoid elastic plus nonlinear geom will be used to approximate the inelastic plus nonlinear geom. This is more work, right? More work to do. If you want to do inelastic analysis, your frame structure has to be discretized, and you got to put rotational spring to make the cap of the moment capacity, maybe put also in the middle for the rotational spring to make sure that you enable the column buckling properly. So this is painful. Engineer do not like. This one just elastic. Oh, plus nonlinear geometry. What? Bearable. Tolerable. Let's say okay. So this paper could be useful for this day world. Aside from the sigma p concept, this could be useful for us when we conduct the stability analysis of the frame, and this is more precise than the use of the alignment chart. You can modify the tangent stiffness, so you change the elastic modulus value of steel from E to ET from these modified values and then run in elastic nonlinear geometry analysis, and then you just keep iterate until you get the good convergence. I am over time now. This is 10:08. So for this class, I'm gonna upload this onto the YouTube, right? And tomorrow we are going to come back here again for the finite element analysis. Tomorrow we have the coding for the Q elements and homework. I'm gonna explain you about the homework. It's gonna be like taking so much time, and stress smoothing for the Q elements. So there's gonna be a lot of things going on tomorrow. FEM will be at 8 o'clock. Alright. Thanks for joining. See you again tomorrow.